So we are doing the second part of the chapter 11 review, and we did the question 1 to 8. And now we will start with question 9. The question 9 is asking for the orbital diagram of nitrogen. So an orbital diagram is those drawings you do with boxes that represent the orbitals and then arrows that represent the electrons. In one orbital, you can only put 2 electrons maximum, so 2 electrons per box, so 2 arrows per box. And as we said in the previous questions there, you need an arrow up for one of the electron and the other has to have an arrow down. And so first you need to know how many electrons there is in the nitrogen atom. So you go to the periodic table, you find nitrogen. Nitrogen is atomic number 7 in group 7A, 5A, sorry. So atomic number 7 means it has 7 protons in its nucleus and 7 electrons when it's the neutral nitrogen atom. So we can write this like this, N equal N with a Z of 7, right? The atomic number is represented by the capital letter Z. So we have 7 electrons. And the first, so I use the periodic table to do the electron configurations. And, you know, if you know how to use that, it's helpful. So let me explain how we do this. How do we use the periodic table to do electron configurations? So remember how the rows, you know, the 1, 2, 3, up to 7 here on the left side, the rows are what we call the periods, and they represent the shells. So they represent shells. So the nucleus would be above, you know, above the periodic table, and then you add shells, you know, row 1, row 2, row 3 is the third shell, etc. And the number of electrons you can put per shells increases, right? You see that in the first shell, you can only put 2 electrons, and that they are represented by hydrogen and helium. Then in the second shell, you can put up to 8 electrons, you know, 2 in represented by lithium and beryllium, and then from boron to neon, you can get up to 8. Period 3, again 8, but what is not showing up here is that the 3 d orbitals are actually in period 4. So let me switch and go into a different drawing here. So this is a periodic table that you can use to help you see that. This represents the what we call blocks. And so the 2 first columns on the left, you know, group 1A and 2A are the S block. There is 2 columns in the S block because you can put 2 electrons maximum in a S orbital, right? Remember how the S orbital is just one spherical orbital, and because you can put 2 electrons maximum in an orbital, so 1 and 2 columns or groups to put 2 electrons in the S orbitals. So whenever you are there, it's when you are filling the S orbital. Then when you are in period 2, from the 2s orbital, you go into the 2p orbital. But the 2p here are on the right side of the periodic table, and they are represented by those 6 columns to the right, from group 3a to 8a. And there is 6 column because you can put 6 electrons in total in a p orbital, in p orbitals, because there are 3 p orbitals times 2 electrons maximum per orbital. That's 6 electrons that you can put in a p orbital, you know, p subshell, I should say. So this blue here represents the p block or the p subshells when you are filling them. Then when we were in the third shell, we fill the 3s, then the 3p, and then after we have filled the 3p, we have to start filling the 4s, because we fill in order of energy, and the 4s orbital is lower in energy than the 3d orbital, because the shells overlap. The third shell and the fourth shell overlap, and the 3d subshell is higher in energy than the 4s subshell. So you will need to fill the 4s before you fill the 3d, and that's why the 3d appears here after the 4s and before the 4p. And so this aqua blue or green blue represents the D block. There is 10 colons in the D block because there is 5 d orbitals times 2 electrons max. So you can put a maximum of 10 electrons in a d orbital. So that's why there is 10 colons for the D block. And then once you fill the 3D, you can fill the 4P. And then you go down one row again and go into the 5 period and fill the 4s and then the 4d, because again there is overlap between the 5th shell and the 4th shell. And then from the 4d you go to the 5p. And it's when you reach the period 6 and period 7 that you will fill the f orbitals. The f subshell contains 7 f orbitals times 2 electrons each. That's 14 electrons that you can put in a f subshell. And that's why those 2 rows here at the bottom, the lanthanide series and actinide series, have 14 colons. 14 because you can put 14 electrons in total in a f subshell. And remember how these 2 rows should be in period 6 and 7 between the S block and the D block. Really, the periodic table should be much wider. You should have the S block, then the F block, at the level of period 6 and 7, then the D block, from period 4 to 7, and then the P block from period 2 to 7. So it should be much wider. So you have to remember filling the f orbitals, when you are in period 6 and 7. Anyway, let me show you how we fill the electrons in the, up to the element using this periodic table. So first you will, I have to do the arrows this way. First you place 1 electron in, in the box of hydrogen, then 2 electrons in the box of helium. So at that point, oops, not this. Should undo that. So once you fill the first shell, you have 1s2 is the electron configuration up to now. From the first shell or first period, you go into the second period, and you will do 1 step in lithium and the second step in beryllium. And at that point, you can write that your electron configuration would have 2s2 on top of the 1s2. So we have 1s2, 2s2, and that's 4 electrons in total. And then we go into the p block up to nitrogen. And that adds 1, 2, 3 electrons. So, and here we are in the 2p3. So that would be the 2p3. That ends the nitrogen electron configuration. So let me go back to the question here. Okay, so we have 1s2, 2s2, 2p3. That's the electron configuration of nitrogen. But here the question is asking for the orbital diagram. So you need to draw those boxes. And it's done here for us because it would take too much time otherwise. So you do 1 box for the 1s and put 2 arrows, 1 arrow up, 1 arrow down, always. Then another box separate from the 1s, and that's going to be the 2s, just one box with two arrows, one arrow up, one arrow down. That's 4 electrons. Then you draw 3 boxes together. They have to be together because there is 3 p orbitals in a p subshell. So you draw those 3 p orbitals next to each other, and you will fill them one at a time with 1 electron first. So that means you place 1 arrow up in the first box, another arrow up in the second box, and then a third arrow up in the third box. And at that point, we have reached our number of 7 electrons in total. So you need to stop. And you see that this way, the nitrogen has 3 arrows up in the 2p subshell. They should not be paired. You have to do arrow up and fill each orbital before you pair the electrons. So this is a very important thing. You know, when you have orbitals of the same energy, like those 2p here, fill the orbitals singly, which means 1 electron at a time, before you pair electrons. Only pair electrons after each orbital of the same energy are half full. So you need to pair, for example, if you have 8 electrons, you would start to pair in the first box of the 2p here. So this is important because these, you know, the fact that you have 3 electrons with arrow up in the nitrogen atom here, you know, can give magnetic properties to the atom. So this is why it is an important, you know, specificity here that you need to pay attention to.
Yeah.
Write the ground state electron configuration for sulfur and write its noble gas electron configuration. So you may wonder, why is it saying ground state electron configuration? So ground state here is just saying that you take sulfur in its neutral state and its not excited state, right? Because as you learned in chapter 11, atoms can gain energy and then the electrons will move up into levels, you know, higher levels, and they will be in what we call excited state. And then the electron configuration would look different. So that's why every time you are asked an electron configuration, it's always for the ground state, which means when electrons are all, you know, in the lower energy levels packed on the bottom, if you will. So to do that, we need to look for how many electrons there is in sulfur. So we go to the periodic table and find sulfur. Sulfur is there, atomic number 16. So it has 16 protons in its nucleus and 16 electrons in the, you know, electron cloud. And so to do the electron configuration, you do the same as what you did for nitrogen. And so here we can already say we have, you know, we go into period 1 and fill with 2 electrons, and we have the 1s2. Then fill 2 electrons in the 2s2. And then the 2p will be filled this time with, instead of 2p3, it's going to be 2p6, because here we need to fill the 2p orbital completely. So with 2p6 electrons. From there, you go down 1 period and you fill the, you know, here from sodium to magnesium, and that will be 3. So 3s2. The 3 comes from the period number. S, you know, is the S block, and then 2 electrons in that. And then from there, from magnesium, you still have not reached sulfur, so you can continue. And then here there is no D block. You go directly into the P block until you reach sulfur. So it's 1, 2, 3, 4 step into the 3p orbital. So 3p 4 steps. So 3p4. Let me make this smaller. And so that would be the electron configuration for sulfur. So let's write it completely here. So sulfur, atomic number 16. So we have 16 electrons in total to distribute. The electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. So that's the ground state electron configuration. Now we need to write its noble gas electron configuration. So the noble gas electron configuration allows you to write electron configuration in a more condensed way, because you see that, you know, if each time, you know, for atoms, for example, like livermorium at the bottom here, each time you have to go and start from, you know, the first period, 1s2, 2s2, 2p6, 3s2, 3p4, 3p6, etc. So it becomes very, very long. So we have this shorthand way of writing it that, you know, makes it easier. And it's using the previous noble gas from the atom you have. And so here we are with sulfur. So you need to find the previous noble gas from sulfur. So the previous noble gas from sulfur is neon, right? It's the one in the period above. So then you would start the electron configuration with neon, and you write it in brackets. And those and the neon in bracket will represent the first 10 electrons, because you see how neon has 10 electrons, you know, right? It's here. Oops. Neon has 10, atomic number 10, which means it has 10 electrons. So neon in brackets will represent the first 10 electrons. So that eliminates the 1s2, 2s2, 2p6, because that's 10 electrons up to that. So you remove that, and then you keep the rest. You keep the 3s2. So from neon, you go into sodium, magnesium. So that's a 3s2, and then 3p4. So that means the noble gas electron configuration of sulfur would be that. Neon, 3s2, 3p4. And again, you can use the periodic table very easily to write those electron configurations. Question 11, write the electron configuration of aluminium 3+. So here you have to be careful. It's an ion, right? It's aluminum 3+, not aluminum, not the neutral atom, but the ion aluminum 3+. So here, let's erase some of the stuff here. Aluminum is here, atomic number 13. So Z equals 13. And we need the electron configuration. So that means not the noble gas one, so not the one with the neon. So you have to be careful. It's aluminum 3+, which means it's not exactly 13 electrons, right? Aluminum, when it became the aluminum ion 3+, it lost 3 electrons, because those 3 positive charges, they come from the fact that you have 3 protons in excess in the nucleus compared to the number of electrons. So you have 13 protons still, because it's still aluminum, and you have only 10 electrons. So you remove 1, 2, 3 electrons, and that means you have 10 electrons. So let's look at this. So you start with aluminum, atomic number 13. But aluminum lost 3 electrons to become Al3+, which means 13 minus 3, 10 electrons in Al3+. 10 electrons means it's actually the electron configuration of neon, right? If you look here, 10 electrons corresponds to neon. So then it's going to be 1s2, 2s2, 2p6. And that's the electron configuration of Al3+. But that's also the electron configuration of neon. And so we say that aluminum 3+ is isoelectronic to neon. Isoelectronic, again, means that it has the same number of electrons as neon. Iso means the same in Greek, and electronic refers to electrons. So same number of electrons as neon. Question 12. What is the element represented by this orbital diagram? Okay, so we have argon in brackets. So argon here represents all the electrons up to, so let's look at argon, up to 18, because argon is atomic number 18. So argon here represents the first 18 electrons. Then we have 4s2 with 2 electrons and the 3d5 with 5 electrons. So if we count 18 plus 2 electrons, that's 20, plus 5 electrons, that's 25. So the element we are looking for is atomic number 25. So let's look here. Atomic number 25 is manganese. Manganese is atomic number 25. So that means this orbital diagram represents manganese, right? Because of the number of electrons. So I want you to notice how here we had 4s2, but then 3d5 afterwards. This is the correct order. Even though the 3 here indicates a lower shell, it will be filled after the 4s because the 4s is lower in energy than the 3d. The two shells overlap, and then that's why you start filling the 4s before you finish filling the 3d. And when you are using the periodic table to write this kind of electron configuration where you have, you know, when you reach the fourth shell here. So you saw up to now, we use the period number for the S and the P subshells, right? But when you reach the D block and the F block, you have to be very careful. When you reach the D block, like here for manganese, so you would, so if we do the full electron configuration and we already have 1s2, 2s2, 2p6, 3s2 drawn here. So you would go to, actually, I have to do it the other way. Sorry. So then you fill the 3p with 6 electrons, right? 3p. We use the period number for the p subshell. When you go down one period, you are on the 4s here, S block. So 4s2. Let me write this here. So you would have or above, or here 4s2, 4s2. So you would write this as 4s2. Up to that point. And then to reach manganese, we saw it's 3d10, right? And 3d10 here. 3d, not 10, 5, sorry. 3d5. Okay. Why did we use 3 in front of the d instead of 4? Because we are in the fourth period. Well, again, it has to do with the fact that the 3D is higher in energy than the 4S. And that's, you know, the way orbitals are. And because of that, when you use the periodic table to write an electron configuration, when you are in the D block, you need to do the period number -1. So period number -1 for the D. So when you are in the D block. And you will see that when you are in the F block, you will have to do the period number -2. So for F, it's even 2 that you need to remove from the period number. So let's see some examples of that with the next questions. Well, actually, we have a question 13 here that is about something else. What do we call elements whose electron configuration ends in NS2 and P5? So electron configurations for elements that are in the same group, so which means same columns, right? They end in the same type of electron configuration. And here we say NS2 and P5. The N represents the period number. And so if you change that by 2, it doesn't start with 1, but if you start with n equal 2, so ns2 and p5, where would that be? ns2 and p5. ns2 and p5, let me remove stuff here. ns2 and p5 would be here, ns2, and then np5 would be here, fluorine, right? That's where you will have fluorine. And now if we change the n by 3, ns2 np5 with 3, so 3s2 3p5, that would be the chlorine, right? 5 electrons in the chlorine. So 1, 2, 3, 4, 5 electrons in the 3p. So 3p5. And then again, ns2 and p5 with n equal 4. That's going to be 4s2, 4p5. And that would be bromine. And then etc. If you change n by 5, that would be iodine. So you see that any electron configuration that ends in ns2 and p5 is actually all elements from group 7a, right? So, and group 7a have a particular name. They are called halogens. So that's what is the answer here. Group 7a have these electron configurations and they are called halogens. See how this is spelled? So, and n equal 2 for F, we saw that. N equals 3 for chlorine, n equal 4 for bromine, and n equal 5 for iodine. That's the 3 main halogens. Notice how the 3D and 4D orbitals are omitted from the ns2 and p5 way of writing the electron configurations. Because even though they are the d orbitals, even though they are higher in energy than the corresponding s orbital, they are still from the previous shell. So they don't matter as far as when we are looking at valence electrons. So that's why we tend to just omit the d orbitals from this way of writing. So now, what is the noble gas electron configuration of polonium? So polonium. So let me clean up here. So polonium is here, atomic number 84, right? In group 6A, sorry, 6A. So you need the number of electrons, so 84. And we are asked to write the noble gas electron configuration. So that means we don't need to do the full ground state electron configuration, right? We can start with the noble gas, that is the noble gas before polonium. So let's look at the periodic table. The noble gas before polonium is xenon. So xenon is going to be in parentheses, or sorry, in brackets. So xenon will represent the first 54 electrons, right? You see how atomic number is 54 for xenon. So we need to add 30 more electrons, after that, right? Because from 84 to 54, there is 30 electrons more in polonium. So from xenon, if you use the periodic table here, you can see that you will need to be going into the 6s subshell, right? So that's going to be 6s2 at that point. So let me use those things here, 6s2. 6s2. Then you go into the D block, but there is also the F block there. Remember how I told you these two inner transitions metal, inner transition metals, they should be in period 6 and 7. And they should be between the S block and the D block. So here, because we will need to go all the way to polonium, we need to fill the F and then the D. And then we will go into the P subshell because polonium is in the P subshell. So before we do the D, we need to do the F. And I told you when you need to do the F, you do the period number -2. So 6 minus 2 is 4. So it's going to be the 4 F orbitals. And that corresponds, and let me use that arrow here. That corresponds to this full width of the inner transition metals here. From cerium all the way to lutetium. And so that's going to be 4F. Let me use that. So 4F and 14, right? There is 14 colons in there. And so you need to add 14 electrons in the 4F. From there, you're back here in the D block. And so we will then do the full D block all the way to mercury, right? Be careful, the D block stops where the B group stops. And let me use this here. And that's going to be, so for D, we said it's the period number -1. So 6 minus 1 is 5. D, and here we're filling it completely, so 5D10. 5D10. And then we are finishing with the P block here until we reach polonium. And that will be here. So you go back to the period number. So 6, here, 6, P, and there is 4 electrons up to polonium, 6P4. And that finishes your electron configuration for polonium. So let's see how it looks like. So xenon, 6s2, 4f14, 5d10, and 6p4. And if you count the number of electrons, you should have 84. So we have 54 from xenon plus, let me take this bigger. So 54 from xenon plus 2, that's 56, plus 14, 56 plus 14, that's 60, 70, 70, plus 10, 80, plus 4, that's 84. So that's correct. We have our 84 electrons there. So be aware that if you look if you are using Google, for example, to do your electron configurations, this may not be written exactly the same way. And I will consider it wrong if it comes from Google. You need to do it by yourself the way I teach you here. So be aware of that. It will not be considered correct if it's not in this way of filling first the F and then the D and then the P. It should be in that order. So let's practice some more with the electron configuration of plutonium. Again, noble gas electron configuration of plutonium. Let's look at plutonium. Plutonium is an inner transition metal in the actinide here. That's the actinide. The row above are called the lanthanide. So plutonium atomic number 94. So we need to fill up to 94 electrons there. First, we need to find its previous noble gas. So let me clean this up. So we are, plutonium here is in period 7 because you see it's in the lower row. So that corresponds to period 7 here. So it would be here. So the previous noble gas is radon. So from radon, radon represents the first 86 electrons. From radon, we go into the 7 here. So that's going to be 7s2, right? From 7s2, we are going into the F because it looks like here we are going into the D, but it's not the way I want you to do it. I want you to have the F block between the S block and the D block. So it really starts right after the S2. I want you to feel the F orbitals. And so that means you go into thorium, protactinium, uranium, neptunium, up to plutonium. And then there is one step here due to the actinium. So that's how many? 1 for the actinium, 2, 3, 4, 5, 6 steps until you reach plutonium. Sorry. So it's going to be. And so what's the number in front? Because we are in period 7, so you do 7 minus 2 is 5. So 5 is correct here. F, and we said 6, 5F6. Right? So from radon, 7s2, and then 5f6, and then you have plutonium. There is no d orbital field here. So radon, 7s2, 5f6. That would be the noble gas electron configuration of plutonium. Okay, we have reached question 16. Arrange the following sets of elements in order of increasing atomic size. And that's the first set here. We have PB, BA, CS, AT. Let's look at where these are in the periodic table. So PB, what was it? We had CS, BA, and astatine. So astatine, PB, BA, barium. So it looks like they are all in the same period, right? Period 6. So we have cesium, barium, lead, and astatine. They are all in the same period, and we need to order them in order of increasing atomic size. So here we are in the same period, so that means we are filling the 6th shell. So you're putting more and more electrons in the electron cloud and protons in the nucleus of the electrons in the 6th shell. So the shell should not increase, right? It's still the same shell. However, this is not an intuitive. This is not intuitive the way the size changes, because here from left to right. So from left to right. Let me use this arrow. So from left to right. From left to right of the periodic table, the size of the atoms decreases. So atomic size decreases. Atomic size decreases. And that's not intuitive, right? You would think, okay, you put more protons and electrons and the size should increase. But no, it actually decreases the size of the shell, the 6th shell. Why? Because you're adding more protons as you go from cesium to astatine. You're adding more protons in the nucleus and more electrons in the 6th shell. And so there is more attractions between positive charges from the protons and negative charges from the electrons. And so it increases the attraction because there is more and more strength to the attractions due to the fact that you add positive and negative charges. And so that means the nucleus will be able to attract more strongly the electrons. And that will reduce the size of the shell, the valence shell, which is the 6th shell here. And because remember how the size of an atom is due to the valence shell, right? It's the electron who determines the size of the atom, by filling shells. And the valence shell, which is the outermost shell, will determine the size of the atom. And then it's held more strongly by the nucleus, the more you add protons into the nucleus. So the size is actually decreasing from cesium to astatine. And here we needed to do from increasing atomic size. So from a smaller atom to larger atom, first you have astatine is the smaller atom, then lead, then barium, and then cesium. It follows the row. But it increases from astatine to cesium. Cesium is actually a larger atom than astatine. So now let's look at the second series of elements here. We have cesium, potassium, and lithium. Cesium, potassium, and lithium. So K is potassium and lithium. Li is lithium. And so the size, so here it's intuitive. It goes as we expect. The size in, oh, the arrows are oriented the wrong way. So the size increases as you go down the column. Atomic size increases. So atomic size increases as you go down a column or down a group, because as you can see, those little numbers, the 1, 2, 3, 4, 5, 6, 7, indicates the number of shells that you are adding, around the nucleus. And so you can see an atom with 2 shells will be smaller than an atom with 4 shells, than an atom with 6 shells. So this is more intuitive and easier to remember. So that means if we order them in order of increasing atomic size, then lithium will be the smaller atom, potassium, and then cesium, the larger atom. Let's go through question 17. Arrange the following sets of elements in order of increasing ionization energy. So we have germanium, S for sulfur, F for fluorine, Rb is rubidium, and then Mn is manganese. We need to order them in order of increasing ionization energy. So let's define what is ionization energy first. Ionization energy is the energy needed to remove one electron from the neutral atom, and the atom has to be in the gas state. You don't have to remember this, but that's the energy needed to remove one electron from the neutral atom. And so ionization energy is actually varying in opposite direction than the atomic size. So when you have learned how atomic size varies, then it's the opposite for the ionization energy. Because the smaller the atom, the stronger the electrons are pulled by the nucleus, and the stronger the electrons are held by the nucleus, right? So a smaller atom will have, it will have the electrons closer to the nucleus, and the nucleus will have a stronger force of attraction towards the negative electrons, right? So it's due to the positive and negative attraction between the protons and the electrons. So it is harder to remove an electron from a small atom because it's held more strongly by the nucleus. So smaller atoms will have large ionization energy, and large atoms will have smaller ionization energy. So here, another thing that you can use to remember that, how it varies. We know that metals tend to give away their valence electrons easily because they like to become positive ions, to be like the previous noble gas, right? Metals, remember how they are in the left side of the periodic table. They like to give away their valence electrons to be like the next noble gas because they have few valence electrons, so it is easier to get rid of those few valence electrons and be like the next noble gas. So that will make them willing to give away an electron. So their ionization energy will be small. Non-metals, on the other hand, so non-metals are in the upper right corner, right? Carbon, nitrogen, fluorine, the noble gases, the halogens, etc. They tend to gain electrons easily. They like to become negative ions. We've learned that now. And so they are really not willing to lose electrons. They actually prefer to gain electrons and become negative ions. So their ionization energy will be large. So overall, you can remember that the ionization energy will vary this way. The arrow is upside down. Actually, like this. So ionization energy will vary like this. Ionization energy increases, from the lower left corner, from francium to fluorine, increasing from Fr to F. That's what you want to remember. Ionization energy increases, from francium to fluorine. Yes, fluorine and not helium, neon, argon, or these noble gases, because noble gases, they really don't like to become ions, and it's really, really hard to remove an electron from them. So we usually don't talk about these elements when we are talking about ionization energy, but they have the highest ionization energy of all because they're so stable when they are neutral, and they are really not willing to either give away an electron or gain an electron. So then if we look at our atoms here, let's select them. We have germanium, sulfur, fluorine, rubidium, and manganese. So we have germanium, we have sulfur, fluorine, and manganese here, right? Germanium, sulfur, rubidium as well. Rubidium is here. It's group number 1A, an alkali earth, an alkali metal, not an alkaline earth, an alkali metal. Okay, so we have our atoms there. So so you see the arrow, how it shows you the way you should arrange them, right? We need to arrange them in order of increasing atomic ionization energy. So there we go. We will start with rubidium, manganese, germanium, sulfur, fluorine. So that's how you want to, yes, rubidium, manganese, germanium, sulfur, and fluorine will have the highest. So here it's the side of the higher ionization energy.